Any questions? Everything is crystal clear. All right. Okay, so we are getting towards the end of this course. There is only a single topic that we're going to deal with, and that is undecidability. There are no exercise sets for that, so you'll just have to pay attention. Let's start with the following question. Suppose I have a Turing machine. And it has some input, and it says yes or no. Now, that, of course, is sort of the idea that we have inherited from finite automata and push-down automata. For all practical purposes, we have the expectation that things terminate with a definite answer, yes or no. Now, that is clearly the case for finite automata, because in every transition you consume a letter of the input, and as such, if the input has n letters, the finite automaton will have n transitions, and after that we can determine whether or not the word is accepted. But more importantly, for what we're now going to look at is, we certainly know that the finite automaton terminates. It will stop. There's nothing else to be processed. Now, that is not entirely true for a push-down automaton. It is, of course, conceivable that you come up with a push-down automaton that reads epsilon and puts something on the stack for every epsilon that it reads, and so your stack will get larger and larger and larger, but you're not consuming more of the word because you're only reading epsilon. So in some sense, we already have the issue of whether the push-down automaton will terminate or not. Now, in this particular case, it's relatively easy to see that it will either go on forever or it will stop. And so from that point of view, it is not that hard a question to determine whether the push-down automaton will terminate or not. And even if it doesn't, then it is quite clear that it may, you can determine yes or no. Now, when it comes to Turing machines, things are quite a bit more complicated. It is conceivable that the Turing machine will not halt. That a Turing machine will not halt for some input. Now, that is a problematic statement, because clearly if the Turing machine halts, it halts. We know, and it may accept or it may reject, it may not be able to continue moving. And so from that point of view, it will halt one way or another. But if it doesn't halt, we don't really know why it doesn't halt. The important consideration here is that just because you haven't gotten to a situation, to a configuration where the Turing machine halts, doesn't mean that you will not get to such a configuration. We don't really know if we just made another 10 or 100 or 1,000 or 1,000,000 moves. Maybe it will terminate. Maybe it will halt. And so the question then is it possible that it does not halt? So this says conceivable, but of course the question is, are there Turing machines for which we cannot determine whether it will halt? And so before we get to that, before we resolve that question, let's play a little bit of a game. This is we're defining a terminology. And we're going to say a language is recursive if there exists a Turing machine that halts for every input. And accepts L. If that's the case, we call that language recursive. Now, if we don't know that such a Turing machine exists, then we are looking at a different concept. The language L is recursively enumerable and since this is way too long a term, it is usually called RE, recursively enumerable. If there exists a Turing machine that accepts every word in L and does not accept any word not in L. Now, of course, the question of acceptance implies halting. However, does not accept that second part of the definition does not necessarily imply halting. I am not here saying that it explicitly rejects. That's a very subtle difference. It is a question. Well, if it were to explicitly reject by, for instance, having a move that is not defined, so in that case, obviously, it fails to accept, but at the same time, it obviously terminates, because once you can't move anymore, then you obviously halt. But that's not really the case necessarily when we're talking about the Turing machine does not accept. It simply does not accept. We keep on going and it does not accept. We keep on going, it does not accept. It does not reject. So there is a subtle difference that is crucial to all that discussion, that does not accept does not imply halts. This does not imply halt. It could just go on. If it keeps on going, then it certainly will not accept. Now, obviously, there are words that may be explicitly rejected, at which point the Turing machine halts and says, no, this isn't going to work for that particular word. Remember, Turing machines, as we defined them, are deterministic, so you don't really have to make a determination whether there is a sequence of moves. There is one sequence of moves that the word is going to, the input is going to define. But what is important here is that the issue that something is not accepted doesn't imply that the Turing machine actually halts. It may just continue spinning its wheels. In some cases, may be quite obvious that this will never get anywhere if it keeps circling around and going around the same way indefinitely. Then obviously this is it will be clear that it will not halt, even though you can then obviously conclude that it is not going to accept. But what is important here is that the fact that the Turing machine does not accept does not necessarily imply that the Turing machine halts. So what we now then have is we have the notion of recursiveness. Language is recursive if there exists a Turing machine that will halt for any input and of course accepts the language. And then we have the notion of recursively enumerable, which says, well, it obviously will accept every word in the language that supposedly is defined by that Turing machine. But we're not really making any statement about whether the Turing machine will halt for words that aren't in the language. And so we have essentially three possibilities. A language could be recursive. A language could be recursively enumerable. Or a language could be not RE. Those are the only three possibilities that we have. If you think about it, if it's recursive, then obviously it will halt. There is a Turing machine that will halt on any input and accepts that language. If it is recursively enumerable, you have a Turing machine that will halt for every word in the language, but we are not making any statement about what happens if not in the language. And then, of course, we have the issue that there may not be a Turing machine for that language. We've said, if you recall early on, that there are uncountably many languages, and obviously any description, so for example, in particular, a description using a Turing machine is obviously out of a countable set, because every description is a word over an alphabet that involves the symbols that are being used to describe the Turing machine, and therefore it is a finite word, which means the set of all these finite words, the set of all these descriptions of Turing machines is obviously countable. And so clearly there are many, many more languages that are not countable than there are languages that are countable, that can be defined using, for example, Turing machines. And so there is certainly that third possibility. And now the question arises, what can we say about this weird category RE? And in particular, well, what if we say RE but not recursive? This is what we're going to be interested in. And of course, it should be fairly obvious that every recursive language is RE. Because obviously, if you just reread the definition, if it halts for every Turing, if the Turing machine halts for every input and accepts L, then obviously then there exists a Turing machine that accepts every word in the language and does not accept any word not in L. Well, if it is recursive, then obviously at that point it will halt. So clearly, recursive is a subset of recursively enumerable. So the question then really is, we obviously can see that recursive Turing machine always halts. Non-RE, there is no Turing machine that accepts that word. That's a fairly straightforward dichotomy. The question is about this RE. This is, of course, sort of a weird category, and in particular, we would like to look at, can there be languages that are RE but not recursive? Now, if the answer is no, then everything is very simple. But I wouldn't be spending this week talking about this if it were that simple. So you can already surmise that, yes, this is a can of worms that we're opening up here. So let's look at these three categories. And let's look at what happens if we have two Turing machines, one for the language. We have M for L, and we have M prime for L complement. So now we're looking at the language, L, and we're looking at its complement. Obviously, this whole notion here that we talked about, recursively enumerable, there exists a Turing machine that accepts every word in L and does not accept any word not in L. Well, if we had a Turing machine for the complement, then it will accept any word not in L and does not accept any word in L. That would be a Turing machine for the complement, so that would be M prime. And now let's assume what can happen depending on whether these two Turing machines are recursive or RE. Now, obviously, it is conceivable that both languages are not RE, in which case there are no Turing machines. So in this case, we are assuming that at a minimum M and, well, L and L complement are recursively enumerable. That is consequence of the fact that we're assuming we have these two Turing machines, M and M prime, one for L and one for L complement. So they're both obviously recursively enumerable. And so what can we conclude if both M and M prime are recursively enumerable? Well, what we can do is, if we assume that these Turing machines, M and M prime, halt for the language that they define, and we don't really know anything about what happens for the words that are not in the language that they define. So M is a Turing machine that is going to halt for every word in L. And M prime is a Turing machine that will halt for every word not in L, because it defines L complement. And so what we can do is we can construct a new Turing machine where we input a word, W, which then gets distributed to those two Turing machines, M and M prime. And if M says yes, then we say yes. If M prime says yes, then we say no. And we can see, because M is guaranteed to halt, being RE, for every word in L. So if W is in L, then M will halt. Conversely, if W is not in L, then it is in L complement, and in that case M prime will halt and say yes. And so that then proves fairly straightforwardly that if we have Turing machines for a language and its complement, if L and L complement are RE, then L is recursive. Recursive means it will halt, and we will know, yes, the word is in the language, or no, the word is not in the language. And so what that means is that if we happen to know that we have a Turing machine for a language L, and we also have a Turing machine for a language L complement, for the complement of that language, then necessarily it follows that L is not just RE, it is recursive, because I explicitly constructed here that Turing machine that is guaranteed to halt for every word, whether it is in the language L or not. And so in this case, this is now a recursive. This is a Turing machine that halts. On every input. So what that means is that if we have a language, then there are the following possibilities. L is recursive. And L complement is recursive. L may be RE, but not recursive. What can we then say about L complement? That is, of course, the tricky question. If it turned out, and of course we don't know yet whether there are such languages, but if we assume logically that we have a language that is RE but not recursive, what can we immediately say about L complement? Well, it's not recursive. That is true, but that's if L complement were not if L complement were recursive, then obviously L is recursive. Right. It is not recursively enumerable. If L is recursively enumerable, I'm sorry, but not recursive. Sorry. I said not, but I didn't write it. So if L is recursively enumerable but not recursive, then L complement is not recursively enumerable. That follows fairly directly if we assume that, well, that's wrong. L complement is not recursively enumerable is wrong, so L complement would be recursively enumerable. That would be the opposite. And so L is recursively enumerable, L complement is recursively enumerable. So we're back to this diagram, which of course then would be immediately a contradiction to the whole point that L is not recursive. So that is a strange conclusion, but it follows directly from this little drawing, that if we were to assume that there is a language that is recursively recursively enumerable but not recursive, then the complement of that language cannot be recursively enumerable. So if we have a Turing machine for which if we have a language for which every Turing machine may not halt on words that are not in the language, then the complement of that language is such that no Turing machine can exist for that language. That's what non-RE means. There is no Turing machine for that language, and so that's, of course, a possibility. And the third possibility is L is not RE. Well, in that case, then L complement is either not RE or RE but not recursive. That, of course, is, if both of them are not RE, then, well, that's just the way it goes. And the second case, L complement is RE but not recursive. That is, of course, simply a restatement of that case B. If L is RE but not recursive, then L complement is not RE. Well, if we throw in another complementation, then we have L complement is not RE but not recursive, which case L complement, which is L, is not RE. So these are the three possibilities, and the one that is the most intriguing is, of course, that B part, that there is a language that is recursively enumerable but not recursive, in which case no Turing machine may exist for its complement. So that is a bit strange. Of course, we have at this point nothing that would prove that such a language exists. Okay, this is just a logical fun and game stuff where we assume a language is RE but not recursive, in which case we logically conclude that its complement can't be recursively enumerable. But at this point, we don't know whether such a language in fact exists. If it turns out that no such language exists, everything that we've talked about is certainly correct. Okay, nothing would be, everything that I've said so far would be still valid if such a language were not possible, RE but not recursive. Now, of course, as I said, we are going to show that such a language exists, a language that is RE but not recursive, and that is not entirely trivial. But what that means then is, once we have shown the existence of a language that is conform with that B observation, then we actually know that there are languages that are RE but not recursive, which means that any Turing machine that accepts such a language will not halt for some input that is not in the language. Okay, so let me repeat that. If we can show that there are languages that are RE but not recursive, then any Turing machine for that language, and that of course means that the Turing machine, according to the definition of RE, will accept any word and halt, of course, but does not accept any word not in the L, but it will not halt. Because if it were to halt, then obviously it would mean that the language is recursive, because the Turing machine would then halt on any input. So if such a language, RE but not recursive, exists, then for every Turing machine for that language L, and there of course you can probably come up with an infinite number of Turing machines for a particular language, none of these will be able to halt on every input that is not in the language. It will, of course, halt on every input that is in the language. That is necessarily the case because it has to accept, and when it accepts, as I said, it will halt. But it doesn't, if it deals with a word that turns out not to be in the language, then not only does it not accept that word not in the language, but for some of these words, the Turing machine will not halt. And that is true for any and every Turing machine that does accept this language according to case B. And that, of course, is what we have to show, that such a language does exist. So
Professor?
Yes.
Okay, so I have a question on this because I don't want to get lost, because I feel like I understand what's happening, but I'm not 100% sure. So what we're looking at right now is with this Turing machine that accepts two different languages, one of them being
No. Turing machine will only accept one language.
So the Turing machine itself gives a yes or no on the language.
No, that's not true. The Turing machine will give you a yes.
Okay,
if
so
it gives you a yes or a no, that means the no will have to be reached within a finite number of steps, then it is recursive. If it is not recursive, if all we know it is RE, then the Turing machine will take a word, and if the word happens to be in the language, it will say eventually, yes, that word is in the language. But if the word is not in the language, it may spin its wheels indefinitely. So that's why I'm objecting to your characterization that it will say yes or no. It will say yes if the word is in the language. If you require the Turing machine to say no if the word is not in the language, then you're basically requiring the language to be recursive.
Okay, so does that mean that this machine is actually attempting to look at and make like a definition of what it can and cannot accept, and then based upon...
Well, remember, this is a deterministic device. So there is a single sequence of moves. You provide the Turing machine with an input, you set it to go, and it will go. And it will deterministically follow a sequence of moves. And with luck, that sequence of moves will stop at some point, and either then say yes, that word is accepted, or no, the word is not accepted. Now, if you're not lucky, then the Turing machine will continue working And if the word is in that language, then it will say yes, and at that point, of course, halt. But if the word is not in the language, then there is no requirement for the Turing machine to halt, because that would really mean that you're requiring the Turing machine to be, the language to be recursive, which is, of course, not the case when you're just starting with an arbitrary RE language.
I see. So we're not actually trying to find the boundaries of, like, this machine every once in a while will go on forever. Every so often it'll just continue going forever because it doesn't know to stop, because it doesn't have an edge until.
Correct.
Okay.
It may go on. It may go on forever, and of course you can't wait that long.
Okay. So is this because, like, M naught, or I mean M prime is that much bigger, or is it because M prime is it's
M prime is just another Turing machine,
okay,
which
so
happens to be a Turing machine for the complement. And if you have such a Turing machine, then obviously both L and L complement are recursively enumerable. That's by definition of recursively enumerable, without touching the question whether the Turing machines halt for words not in the language that they're designed for. But of course, if you run these two things in parallel, one of them is guaranteed to halt, because either the word is in the language or the word is not in the language. If it's not in the language, then it's an L complement. If the word is in the language, then M will halt and say yes. If the word is not in L, then of course the word is in L complement, and for that word, the Turing machine M prime will halt and say yes. And so in that case, you have to flip and say no for the overall Turing machine. So in that case, you will get a yes or no. But either of these two Turing machines, by assumption, will only say yes if they can say it, if it is true. So if the word is in L, then M will say yes eventually after a finite number of steps. We don't know how many, but it is a finite number of steps. And if the word is not in L, then it is, of course, in L complement. And for that word, then M prime is going to say yes after a finite number of steps, moves. And in that case, we flip that to no. And so we now have a Turing machine that will halt for every input and will give a yes or no answer. But in general, a Turing machine does not give a yes or no answer. A Turing machine will only give a yes answer if it happens to be a word in the language.
what does this mechanism do for us in terms of, like, power? What are we able to do at the moment? So,
well, once we have shown that there are languages that are RE but not recursive, we then know that the halting problem for Turing machines is undecidable. That is, of course, the implication. So there are problems that are of a nature that we will not be able to answer. And if you recall, a week ago, I gave you the example of the post-correspondence problem. Well, that happens to be an instance of an undecidable problem. I've also given you the question of whether two context-free grammars generate the same language. That happens to be an undecidable problem. In order to be able to show that these problems are undecidable, you actually have to have a baseline. And the baseline in this case is the halting problem for Turing machines. So the question is there a language that is RE but not recursive, is one of the most fundamental questions in algorithms. Because obviously what we're assuming when we design an algorithm is that the algorithm will terminate telling us yay or nay, which is recursive. And the fact that we can show, as we will, that there are problems, that there are languages that are RE, recursively enumerable, but not recursive, means that there are problems that cannot be decided. So it may sound very esoteric, but it is eminently practical, because just think you're trying to solve a problem that happens to be undecidable. Every effort that you're going to spend on that endeavor is going to be a complete waste of your time, because it can't be done. And that whole notion of that certain things can't be done, that is a fundamental problem that is, as I said, somewhat bothersome. People are really feel very uncomfortable with that idea, but that's a fundamental aspect of algorithms, and not every process that allows you to do certain things is actually an algorithm. An algorithm, of course, is something, a description that will always hold. And so you can easily conceive questions. For example, let's just recall the two context-free grammars. Okay, two context-free grammars. Do they generate the same language? Well, that is an undecidable problem. Now, what you can do is you can take the complement. Are those two context-free grammars, are they generating two different languages? Okay, so I haven't proven anything yet, but I'm just giving you an example. So if we're looking at L1, it's the language generated by grammar 1, and L2 is the language generated by grammar 2. Well, what we're really interested in is L1 equal to L2. I haven't proven that yet, and at this point, I still have to show you that there is at least one language that satisfies that B part. But you can easily see that if we were to look at the complement of this question, is L1 different from L2? You can, in fact, come up with a Turing machine, a procedure, not an algorithm, because an algorithm will have to hold yay or nay. But in this case, if you were to ask, are the two languages different, then what you can do is you can enumerate all words. Okay, W1, W2, W3, and so on. And you can test for each of these, each word, W1, is it in L1? Is it in L2? As long as there's concordance, you keep on going, because you haven't found a witness that shows that the two of them are different. At some point, if it were true that L1 is different from L2, there has to be a word that is in, say, L1, but not in L2, or conversely. And you will find that word. And that word then will demonstrate that the two languages are different. So the question whether L1 is different from L2 is RE, because you can come up with a process that will do this kind of thing, and if they're different, you will find that different, a word that verifies that the two languages are different. However, if that's not the case, if L1 actually happens to be equal to L2, then you will go on forever. This will not terminate. There are infinitely many words in the enumeration of all words over the alphabet that underlies the languages. And so there is never going to be an end to that. There's always going to be another word, and you test. Are they both in the same? Are they both in the language, or both not in the language? And the answer is yes. And then you go on to the next word. And so if they are different, then eventually you will hit a word that shows that they're different. But if they're not, then you will never find that word, because there is no such word. And so you can easily see that this is RE, because for L1 different from L2, this is RE because if they are different, then you will find out that they're different. But if they're not different, then this process will keep on going. Now, this is not a proof that this is RE but not recursive, but it is a plausibility argument. You can easily see here a process whereby you will find a witness to the fact that the two languages are different, if indeed they are different. But obviously this process will never terminate if the two languages happen to be equal. Does that shed some light on it? It's a very complicated kind of idea, because we instinctively tend to think that, well, if we have a problem, then we should either be able to say yes or no. And that's not really true. What this whole argument is all about is that just because we can say yes infallibly, this is what that definition says, recursively enumerable if there exists a Turing machine that accepts every word in L. So that is not that difficult to see. That's what we expect. But does not accept any word not in L. We tend to infer instinctively that this idea of does not accept implies that things must halt, and that's not true. And this is where we will actually have to do some work in order to show that there are languages that are recursively enumerable but not recursive. Does that clarify things?
actually does. So is the way that we actually are, we haven't actually done any proofs yet.
We haven't done any proofs yet. At this point, I'm simply telling you what we're looking at and how we're going to do it, and I've given you examples. The equivalence problem of context-free languages, but it doesn't prove anything. At this point, I still owe you a proof that there exists a language that is recursively enumerable but not recursive. I haven't shown that, and I will.
Professor,
Yes.
I have one question.
Yes, go ahead.
Can you hear me?
Yes, I can hear you.
Oh, great. Is that possible? We can draw like recursive and recursive enumerable, not recursive enumerable in the one diagram. I mean the one diagram.
In this one,
Yes.
what we're assuming is that both M and M prime are Turing machines, and so we're assuming that L is recursively enumerable and L complement is recursively enumerable. And if that's the case, then it follows, as I've written down here, that L, and of course L complement, is recursive. So if we happen to have Turing machines that accept L and L complement, halting only if the word is in the corresponding language. So in L for the Turing machine M, and in L complement for the Turing machine M prime, and we're not making any statement about what happens if the word is not in the language that is at issue. So if we have a word for M that is not in L, we don't really know anything. It could stop and say no, it rejects, or it could continue going on. And the same thing for M prime. M prime does not, we're not making any statement of what will happen if we have a word that is not in L complement. Okay. Does that clarify it?
Yes, thank you. Got it. Thank you.
Okay. All right. So what we now have to show is that there is a language that is recursively enumerable, but not recursive. Okay. So we are going to, the next couple of steps are relatively technical. We're going to encode a Turing machine. And so what we're going to have is we have states Q1, Q2, Q3, and so on, say up to QR. These are the states. And we have our tape symbols, X1, X2, and Z. So these are the tape symbols. And we have left and right, which we call D1 is left and D2 is right. And so what we have is that if we have a move Qi xj is equal to Qk xl and dm. So this is a typical move. in the Turing machine. Then this corresponds to the following encoding: 0 to the I, 1, 0 to the J, 1, 0 to the K, 1, 0 to the L, 1, 0 to the M. So in this way, we have encoded the fact that this move, which is a completely arbitrary and general move, we have a state and a tape symbol, which gives us another state, another tape symbol, and left or right. That is then encoded using this string of zeros and ones. And then we can enumerate all these moves, put 2 ones around, and put all moves. And in that way, and I'm not really going into any details because details are just going to obscure rather than illuminate, but you can easily see that all Turing machines can be encoded in this way. So if you have a Turing machine, well, you would have Q1, Q2 through QR, and you would have the tape symbols X1, X2 through blank, and then you have these triples for each of these, if there is one. So you only represent the ones that actually, if there's nothing, then you're not really having any Q1, X2, for instance. So in that way, it follows that you can take this sequence of moves and reconstruct that table, which of course is precisely everything that we need for the Turing machine, because this is obviously this set of states. This is T prime, and then Q1 is going to be the initial state, and final states we need only one, and so there's one specific final state. That is sort of an arbitrary thing, these two things that we have. But it is clear that you can go from back and forth between this definition and the general description of a Turing machine. M, which is of course Q, T, T prime, Q0, and F. Well, we don't really need to differentiate for the representation of the Turing machine between T and T prime. T, of course, is a proper subset of T prime, and so you can easily go back and forth between the sequence of moves that we write down and the actual description, the definition of the Turing machine, and so that means that all Turing machines can be encoded in this way. And now we're getting to the next step. All Turing machines are encountered when enumerating all binary strings. So what I'm saying here is that each Turing machine can be encoded in this way, and that encoding then is a binary string. So if I enumerate all binary strings, I will encounter every Turing machine encoding. So you better think about this. Basically, if you recall, we started out by saying, well, if I have a 0, 1 star, then I can write that down as epsilon 0, 1, 0, 0, 0, 1, 1, 0, 1, 1, and then I go with 3, and then 4, and 5, and so on, of length 3, 4, 5, and so on. And so this is obviously an enumeration. Of 0, 1 star. And each Turing machine encoding, which is a sequence of these encodings of a single move, and there's of course many moves, so all moves together, the totality of all the moves of a Turing machine then is an encoding of a Turing machine. This is an encoding of a move, and so if I write down all the moves for a Turing machine, then I have an encoding of a Turing machine. So all Turing machines can be encoded in this way. And so if I enumerate all binary strings, I necessarily will encounter every single encoding of a Turing machine. And so the next step is I am going to define a language L sub D. This is the set of all words WI. This is, of course, we have an enumeration. W1, W2, W3, WI, such that WI is not in L of MI. So, because I have an enumeration of the strings, binary strings, I will then get an enumeration of all Turing machines. So I have M1, M2, M3, M4, and so on. And so obviously when I look at these binary strings, W1, W2, W3, and so on and so forth, not all of them will in fact correspond to a proper encoding of a Turing machine. There are probably very few. But what is important is that when you enumerate all those binary strings, you will encounter all Turing machines. And that enumeration of all binary strings then induces an enumeration of all Turing machines. So you actually have M1, the first Turing machine, and then you have M2, which is the second Turing machine, in that enumeration of all binary strings, M3, the third one, M4, and so on. So you're going to have all Turing machines that you get that way. And of course, this is an enumeration, but you can obviously then extract from that enumeration the way you tend to picture your Turing machine. So this would be that table. And that then means you actually can define this language. All right, so there is this language. This language says I'm taking a word, the first word, and the first Turing machine in that enumeration, and the second word, the second Turing machine in that enumeration, and so on and so forth. And so basically I have here, this tableau where I have my Turing, my enumeration of the words, W1, W2, W3, W4, and so on and so forth. So this is obviously infinite going that away. And then I have my Turing machines, M1, M2, M3, M4, and so on. And if a word is accepted by that Turing machine, then it will not be in L sub D. So basically, I look at this diagonal W1 and M1, W2 and M2, W3 and M3, W4 and M4. And if that Wi is accepted by Mi, then I have here a yes. Now, I may not know anything here, but if I have a yes here, then I am going to have a yes, false, and then I'm going to flip that. So what I'm saying then is that if I have a yes, then I make a no out of that. If I have a yes, I make a no out of that. If I have a yes, I make a no out of that. And so that is then the LD. And it follows using exactly the same argument that we did when we proved that the languages are uncountable. Set of all languages is uncountable. We had an enumeration of all words, but we can't have an enumeration of all languages. Well, in this case, when we made that proof, we assumed that there was an enumeration of all languages, and then we constructed a language that clearly wasn't among these. Now, in this particular case, we have an enumeration of all Turing machines, but then it follows that this language obviously is not one of those, and therefore LD is not RE. It has to be not RE because it cannot possibly be one of those MIs. Because by definition, we're going to flip, we make this not. Okay? So if LD were accepted by MT, then we're going to look at WT. WT, of course, is in LD. But it is not in L of MT. And so there is your contradiction. So that shows you that this language LD cannot be accepted by any Turing machine by virtue of the way we constructed it, by flipping that yes to no. And so it follows that LD is not RE. Now, that is what we need at this point. So we have now established a Turing, a language that isn't RE. And next time we're going to show that there is a language that is RE but not recursive. But we don't have time for that. So we will come back to that LD. This is the set of all words that are not a WI, that are not accepted by Turing machine, MI. So the ith word in the enumeration is in LD if it is rejected by the ith Turing machine for all I from 1, 2, 3, 4, 5. There are, of course, infinitely many. So LD is not recursively enumerable, and with that, then we can proceed on Wednesday, showing that there is a language that will actually satisfy this issue. So just to give you a little preview, that the LD that I defined here will in fact be that complement. So this L complement, which we've already is LD, is not recursively enumerable, and then we have to show that the complement of LD is recursively enumerable but not recursive, and that is going to happen on Wednesday. Any questions?
Could you go over all the slides?
Certainly. All right, let's see. Slide number 1. Let me see. This is there. Okay. Sorry. Slide number 1. I discovered that it was truncated at the edge. Slide number 2. Slide number 3. Slide number 4. And slide number 5.
Thank you.
Any other questions?
So, Professor, I have another question. Is that only recursive language is hunting or by accepting by the Turing machine?
Say that again.
I mean, is that only like recursive language hunt by the Turing machine, and is the only way to accepted by the Turing machine?
A language is recursive if you have a Turing machine that halts for every input and accepts L. So it will halt if a word is in the language, and of course it will accept that language. And it will halt if a word is not in the language, and it will say, I reject that word.
Oh, okay, got it. So the recursive enumerable in that way is possibly sometimes will be hunt, sometimes will be not hunt, right?
Well, it will halt if the word is in the language. I mean, otherwise it wouldn't define L. So it will halt and accept every word in the language that it defines. But it does not accept, and it does not accept any word not in L, but it may not halt at that point. It may continue spinning its wheels if the word is not in the language. It will have to stop and accept if a word is in the language. But if a word is not in the language, then it may reject it simply by not ever accepting it.
Oh, you mean the recursive enumerable language will separate two situations. If the word is in the language, will be accepted.
It will halt. It will stop. It will say, yes, I accept. But if
okay, got it. Thank you so much. Have a good day.
All right. Any other question? All right, then I will talk to you on Wednesday. Bye-bye.